Hello, my name is Dr. Sergey Sarkisov, and I will be presenting arithmetic series. In other words, we will be looking into adding large sequences of numbers. Okay, and by numbers I'm considering specifically the integers. Okay, so in the set, the Zentrum set, the central set, Z, the integers. Okay, so look at this. Let's actually derive a formula soon enough that will help us add up numbers, crazy numbers. Watch this. So let's look at a problem that you may look into at first and wonder, well, where does this all come about? So look, let's first say 1 plus 2 plus 3. What does that equal to? This is actually called a triangular number, 1 up. And this is equal to, of course, 1 plus 2 is 3 plus 3, so 6, right? And then we go on and maybe have another problem. 1 plus 2 plus 3, and then maybe plus 4. We know that's 10 there, right? 6 plus 4. And then maybe add another 5, and that's what? That is 15. Add another one. Next number 6. 21. And then what? Plus 7. So 28 plus 8. That's what? 36. And plus 9. That's what? 45, right? Okay. So what do we do with all this? Well, that's something we can use a calculator with. We don't need any formula. We could just do this. We did this in our head, right? Now, what if you're asked something different? You're asked to add up more numbers. In fact, many more numbers. One time on a competition in mathematics, I was given a problem similar to the following. Find the sum, evaluate the sum 1 plus 2 plus 3, and it started the same way as you see in the upper problems above, but look, it said dot dot dot, so I'm thinking, hold up, what's going to happen? Well, it goes on, 4, 5, 6, right? And then eventually I see that at the end it says, oh, okay, plus 99, 97, plus 98, and plus 99. And I'm thinking to myself, whoa, wow, that's the sum of the first 99 numbers. In fact, maybe it even said the first 100 numbers, right? And it says, what does that equal to? Wow, so let us look into this problem. This is something I think is very interesting. Let's look at this. So, what do I first think when solving this problem? Do I see any symmetry? Do I see anything that's repeating itself? Something I can, rather than adding a lot of numbers, I know what? Multiplication is a much stronger operation. It acts much more quickly, right? In fact, let me give you a side note here. So, imagine you are trying to see, what's better, counting numbers or, so look, there are some operations, and I want to discuss that quickly. Let's imagine we have maybe a, let's say a 4 by 4 by 4 cube, okay? And so let's say we have, let me lower this just a little bit so we can see something interesting here. We're still talking about numbers here, so look, what if I go and I do this? I have a cube, I connect this, this is one of the faces of the cube, and that we're trying to make here. And so I'm trying to draw a cube, okay? And so you'll see that's one face, the top face, and then we have this front face, and then we will also have the rightmost face, right? Let's see if we can kind of draw it neatly here. So let's do that, okay? And so there's a cube, and look, imagine I break it down into, maybe it's a 4 by 4 by 4 cube. So we have some lines dividing. So we have a lot of unit cubes inside. For example, these are unit squares in the front face, right? You can see there's 4 by 4 of them. But look, let's carefully draw these parallel lines here so we can see what's happening better. And then we even have this one, this one, this one. Nothing else, but let's learn how to draw a cube, right? Let's have some fun with this. Okay. And so we have this, this, this. It's a little bit off, but otherwise it's pretty good. And so we have now a visible kind of cube that's like a 4 by 4 by 4 Rubik's Cube. Imagine that. There are those things, and they're very difficult to work with. Okay, but now, and of course I could give you a little background there where it's like this and then right like that and then like that. You can see a little background. But anyway, how many cubes will I have, right? That's an interesting question. And so we kind of know, most of us know the answer to that. We would have what? Well, let's start counting maybe these cubes. This 1 cube, this 2 cube, 3, 4, right? Let's imagine we just counted them all up, broke them down into little unit cubes and counted them. And we have, so let me say counting. Is that what we want to do? Not really, but it's slow, right? But 1, 2, 3, 4, da 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 da, and so on, and you get somewhere, right? Whatever number that is. Okay. And then also you could and we can make a mistake. Instead of, it's approximately 60, maybe we'd say 60, but maybe we miss a few cubes or whatnot. Let's try addition. And addition subtraction is the next way to go. Sometimes we think that's the kind of the easiest operation, but actually counting is actually something, adding 1 each time is an operation itself. So adding, let's add, look, I see 4 cubes here, right? So what if I see 4 and then plus another 4 plus another 4, right? Look, 1, 4, 2 4s, 3 4s, 4 4s. And I keep going like that because then you go in depth, and then so that's the first face, and then there's another face. So you see there's a first face there, second face right here, and then it continues. There's 4 of them, right? And then whatever that is, right? So we added, and of course 4, 8, 12, 16 is faster than 1, 2, 3, 4, right? So whatever that is, we still could make a mistake. What if we multiply? What does that mean? Multiply. Well, multiply, we can do this. Okay, I can see there are 4 4s. That's what it means. This means 4 times 4, right? And then, of course, plus, I can see 4 4s again, and plus 4 4s again, plus 4 4s again. In fact, you know what that is? That's multiplying, and you can even make it a little easier, because this is adding and multiplying. What if I said, okay, well, this is 4 times, let's distributive property, do distributive property in this. So factor out of 4, and you have 4 plus 4 plus 4 plus 4, which is again 4 4s, and you have 4 times 4 times 4, right? And we can kind of do that. That's 4 times 16, right? And that's what? 64. So we know there's 64 cubes. Probably that's right. In fact, the strongest operation, the more quick one, the quickest one I think to have done would have been to use exponentiation. So exponents, powers in other words. And what I would do here is I would say, okay, well look, the volume of a cube, it's 4 times 4 times 4, right? 4 cubed, that's exponent cubed, the 3, and now that's 64 if you're quick at that. All right, and so we know that's 64 there, and then every one of these had to be the question marks are 64 also. But what I wanted to show you is that, multiplication is stronger than adding or counting, right? Even adding is a little weaker than multiplication. So look at this. Let's get this problem here. Let's do that. Let's take it. And what I'm going to do is this. Let's first do the approach that I first tried, that I first ever attempted to do to find what a sum is equal to. So this is not the way you're typically taught how to do this, but let me show you what I did. And I was happy to get the problem correctly. This is the first time I ever had seen this before, so I felt really creative in doing this. What I did was the following. I thought to myself, okay, look, I have a bunch of numbers added together, but the units digits kind of keep repeating, right? Look, I have 1 plus 2 plus 3 plus 4 plus, right? And it goes on to 8 plus 9. And, I know that is. Who knows what that is? That's 45. We did that above, right? That's equal to 45. But why am I doing that? Because I see, look, okay, next comes a 10 plus an 11 plus a 12 plus a 13. You see how the 2 here and the 2 here, the units digits are underneath each other correctly. 3 and 13, 4 correlates to 14, and so on. Then I have an 18 here and a 19 here. You see that's the next row of numbers. I kind of divided it into rows. And what is that equal to? If you added this up, and you can take some time doing that, you can get 145. How do I know it's 145? You know what I see? I see there are 10 numbers here, right? They're each 10 larger than, there's a 0 here maybe if you wanted to put a 0 here also, kind of to add, just to help yourselves. But you don't need that, but that helps maybe. So look, there are 10 numbers that are 10 larger than the last ones each, so it's 45 plus a 10 times 10, right? 100. Okay, interesting, right? That's how I get the 145. That's already an insightful trick. And then look, then we have 20 plus 21 plus 22 plus 23 plus 24 plus da 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 plus 28 plus 29, and guess what that is going to be? Let's move these a little to the left here so you can see this better. That's going to equal to, again, 45, all the units digits, but now it's plus, I'm seeing 20 every time, right? So it's really 20 times 10, or 2 times 10 times 10, okay? 2 times 100. And so now look, let's go on and on. 30 plus 31 plus 32, that would give us 40. Let's do that, plus 31, and then plus da-da-da-da, and then eventually plus 38 plus 39. You can simplify it some writing, right? It would be 45 plus a 3 of the 100s. Do that. 3 times the 10 times the 10. And then, of course, we can go on, even let's skip a few rows, right? So let's go kind of, you see I'm kind of drawing a little square here in a cell, a sense, 10 by 10 entry, with entries, 10 by 10. And so look, you go all the way to, let's do 90, the last numbers, right? Plus 91, plus 92, plus da-da-da-da-da, plus 98, plus 99. And I think we wanted to get 100 as well, right? So 100 is right here. It's by itself, let's say, because that's an extra number. And so let's see. The 99, well, of course, will be 45 plus 9 of those creatures, the 10 times 10, right? And of course, 100 is equal to 100. Now, instead of me adding, look, I'm going to add all this up, all of these rows and columns of numbers, okay? And so what happens is, look, basically on the left side, I do have 1 plus 2 plus 3 plus, that's the sum I wanted, right? Plus 100 eventually. That's the sum. Let me call it S, if we like, or we just not have anything there. But look, it's equal to what? A bunch of 45s. And how many rows do I have there with 45? 1. So look, the first row has 0 tens. The second row, so there's the first row starts with a 0. The second row starts with 1 10. The third row starts with 2 tens. And it goes from 0 to 9 tens there, right? So that's 10 numbers. So you have 45 times 10. 10 of the 45s. Plus, look, you have a bunch of 100s, right? You have 100, or 10 times 10. And how many of them? Well, you see a 1 there. You see 2 in the third row. You see 3 of them. And you go all the way to 9 of them, right? And later you're going to have one more 100, right? So you're going to have another 100 at the very end, that last number. And we know what 1 plus 2 plus 3 plus da-da-da plus 9 is, right? That's 45. So we have a lot of things repeating. The sum is equal to 450, I mean, right? Plus a 100 times a 45 there, and plus a 100 at the very end. You see, that's what I did, and so it takes some time still. We have a better and a quicker and more efficient approach soon for me to show you. But look, this is 450 plus a 4500, 4500 plus a 100, and that turns out to be 5050. Interestingly enough, that is correct answer here. And that's not something you can just, calculate. At least it's faster than going to calculator 1 plus 2 plus 3. You'd make a mistake somewhere along the way anyway, right? A lot of room for error in that way. Okay, now, here's a way that I would probably see you being taught this more often than not. Here's what you do. You usually let the S equal to, or some sum that you're looking for, let it be some variable or some number. So let's call it denoted with S, the sum. Okay, and let's say we're looking for 1 plus 2 plus 3 plus, and we're doing the same problem. Let's just check if we can get another way of solving it. And then we of course get plus 98 plus 99 plus 100, correct? Okay. So what's another way, maybe a faster way to do this problem? And this is how you do a lot more of these arithmetic sequences and series when you're adding numbers that are equal distances away from each other. For instance, if I say, what are the sum of the odd numbers? And you'll see perfect squares for that. But anyway, so let's do this. We flip the sequence. We flip the sum around. That's the trick. In other words, there's a reason for it, because if it's increasing all the time, what if we make it decrease all the time by the same numbers, the common differences? And so 100 plus 99 plus 98, right? And all the way, let's go down now to, what's that, 3 there, the last 3 numbers, 2 and 1. That's the same, that's identical, right? Just reversal it. So that's also S. And we're looking for that S. Let's add them all up, right? So what is this? 2S, add those equations, is equal to, and now the reason I wanted to show you this also is because, look, this is 101, right? That's what 100 plus 1 is. What's the next number? That's 99 plus 2. That's also 101. Because they go. This one goes up 1. This goes down 1, right? And that's why they're always 101. Now, what happens when I add the same numbers a bunch of times? See, 101, 101, 101 underneath there. That's exactly what? That's exactly one. How many columns do I have of that? I have 100 columns, right? 1, 2, 3, and then it goes on to 98, 99, 100 columns. And so I have 100 of the 101s, which is equal to what? 10,100, right? And so what is S? Divide everything by 2, and you have 10,100 over 2, which is exactly equal to 5,050. Okay? Nice, right? Okay, now, what's the formula in general for the arithmetic series for adding up numbers that are a common difference away? For instance, let me show you another example. What if I did something like this? What if I give you a little bit of different structure here? So what if I give you, okay, find the sum, S is equal to, and you'll be quick with this, let's not even use the formula yet, right? What if I'm adding numbers like a letter like 4 away from each other, and they begin with a -9. So -9 plus, add a 4 to it. Let's start with a negative number, right? We're adding 4s each time. So -5, add a 4 to -5, and you get -1. Add a 4, and you get 3. Add a 4, and you get 7, right? And add a 4, and you go on and on and on. Maybe let's go to 39. You'll see that works. And then I'm seeing a 43 will work as well. Okay, let's just imagine we do all that, right? The first question that I have for you is, how many numbers are there? That's sometimes the trickiest part of this problem. So to find it, let's go ahead and change colors just a little bit. Let's say we're trying to find the sum. And that's the question here. So look, I told you let's reverse the terms, and it's because it's increasing by 4 every time. Let's make it decrease by 4 every time, right? So now let's do 43 plus a 39, and then the other term before that would have been a 35, and so it goes on and on and on, and then plus what are the terms? -5, right? And then -9. And so the reason I'm asking you how many of these are there, that's something we should do on the side soon enough. Because we will want to know how many columns we have, how many times we're adding this same number. And the same number, I mean, add the two equations. You get 2 s's, right? 2 of the sums is equal to what? I'm getting a 34, right? Not -9 plus 43, and then there's a 34 there, and a 34 there, and I'm pretty confident it's going to be 34 every time. Okay, plus 34 plus 34. So it's equal to 34 times something, these two sums. But what something is that? And you know what I do sometimes? I think to myself, okay, well look, on the side here, let's do something here. On the side, I'd say typically, well, -9, what is that? How many, it's just what? It has no 4's added yet, right? Plus 0 times 4. And then -9 plus 1 times 4, that's why we got the -5, okay? And then -9 plus 2 times 4. So I'm interested in how many 4's away is that 43? And that's exactly -1. And so 43, right? What is that? That's -9 plus how many, let's call it n. How many times 4, right? So if we solve for n, I'm going to get 13, because I get 52 here, equals n times 4. Divide by 4, and I get n is equal to 52/4, or 13. Fortunately, an integer, right? Now, you may think, well, there are 13 columns. Well, not really, because the first one had no zeros. In other words, look, you have 0, 1, 2, and then you go to n, which is 13. So how many columns are there really? If I go from 0 to 1 to 2 to 3, and then all the way to 13, so we have 14 numbers. Okay. Here. So that means what? I use 14. So I'm going to do 14 times, and then of course let's go back to that. So 2s is equal to 14 times 34, okay? And so s is equal to, let's divide everything by 2, we get 7 times 34, and I'm seeing that to be 238, right? 210 plus say 28, okay? So wow, that's an interesting sum. We found that in a different way, right? And then how would you find an arithmetic series formula? Okay, how do you find that? How do you keep on adding those numbers and just quickly get a formula going? Watch this. what I would recommend you do is, here's the formula. Let's prove it. Let's write something in general. Let's say, look, first term, call it A1, right? A sub 1, why not? Say sub 1 being first term. How about last term? And how many terms will we have? How about n terms? So A2 would be the second term, A3 would be the third term, A sub n will be the last term. So we have, number of terms is n, right? So this is n, this is an, this is a1. For example, let's say we're given all this. How would we denote this? How would we write this? And let's say common difference, right? We're adding something to the number each time. So common difference. Not that it matters in the formula eventually, but watch. Common difference, we have something there, right? Keep on adding, like I was doing 4 the last time. Common difference equals to d. Let's say difference for d for difference, right? So watch this. The sum that we're looking for is equal to what? A1 plus, well, the next term would have been A1 plus the common difference d, right? It gets larger every time by d. Even if it's positive or negative, it would work, right? And then A1 plus 2d, right? Another d added. And it goes on and on and on to, what is it? It would have been an an minus d, right? The one before it, and then plus an an, the last term. We said that's the last term. So let's think of that, and then rotate the sum around like we did earlier. So we would have what? An here, and plus a an minus d here, right? And so now we're subtracting these, and so it's an minus 2d here, and then all the way to the last terms being a1 plus d and plus a1. And so you may wonder, well, this is messier looking, right? This is, first of all, we have like variables, so we don't have just numbers anymore. It always makes things more complicated, mathematics. But let's do the same thing. Let's add the two equations. We get 2s, and let's look at term by term. We actually know how many columns there are because we know how many numbers there are, right? There are. Let's do this. There are n of them, right? So there's an n. Well, we'll see that in a little bit. But look, how many? So what am I adding? How about a1 plus an, right? Let me make it a little neater here. 1 second. So a1 plus an, okay? And then plus another, look, the d's cancel. See that right there? A1 plus d plus an minus d. And the d's will always cancel this time around. So look, plus a1 times plus n, plus another a1 plus an, and so on and so forth. And we keep on adding plus a1 plus an, and another a1 plus an, right? And we know how many there will be. S, 2 of them, right, is equal to definitely a lot of a1 plus an's. And how many of those are there? N of them, right? Okay. So what is our formula? Let's do the final formula. The sum is equal to the number of terms, n, right, times the sum of the first term plus the last term, okay, all over, right, because we have to divide both sides by 2, all over 2. Wow, right? That is the sum that we were hoping to get. Okay, that's the formula that we wanted to get. And let me put that in a box because it's pretty cool, right? I think that's very cool. Let me do this. Let me put another box here and just make it look a little, put it in there. Just to really kind of emphasize that this is important for us. It's a big, big result. Okay. Interesting, right? So hopefully you like that. And then let me move it even more to the center here. That's our formula. And let's quickly check. Let us check if that really works. So let's go back to a problem we did. How about checking that problem with the first 100 numbers, first 100 natural numbers? So check. If I asked you 1 plus 2 plus 3 plus 4 plus plus 100, right away you can tell me, oh, okay. So how many, what's the first term? A1 is equal to 1. What's the last term? An is equal to 100. And how many do I have? Well, I can see it here. Sometimes that's the most difficult part. This is 100 terms, right? And so what do? I add up the numbers. I add up, but to add up the numbers, what do? I say, okay, well, the sum is equal to the number of terms, 100, times the sum of the first and last. That's 101, right? All over 2, and that's 50 times 101. And that's exactly 5050 or 5050, check mark, right? And by the way, if you want to do a formula like the sum of the first n natural numbers, let's call it a fun formula. Okay, what we can do is find the sum of the first n natural numbers. We can say, okay, 1 plus 2 plus, so let's actually call it, yeah, like n or k. Let's do k this time. So 1 plus 2 plus 3 plus 4 all the way to k, right? What is that equal to? Well, what is that equal to? It's the same thing we did last problem, only instead of 100 we use k. And so look, we plug it in and we say the sum is equal to, okay, the last term is now k, not 100. So we have number of terms is k, number of columns will be k, right? 1, 2, 3, just kind of adding up from 1 to 2 to 3 to k. So we have number of numbers, number of these terms is k, times the first and the last added together, so not 1 plus 100, but 1 plus k, or k plus 1. Let's keep it in the order that you see the formula typically. And now you at least know where it comes from instead of just memorizing it, right? All over 2, right? Because we had 2 sums earlier equal to that. Wonderful, right? That is our formula. Okay, that is our formula for the sum of the first n, or k actually, consecutive numbers. I hope you really enjoyed this little demonstration, and then this formula may help you a lot. Okay, you can even check this on this example I did here with 14 numbers that we were adding 4 each time, right? Right here with the -9, -5, all the way to 43. So I hope you enjoy this video, and I look forward to teaching you more math materials. All right, bye.